So I just want to go a little bit through talking more about what I wanted to talk as well for what we can do additionally. So the next part was after we estimated diversification rates through time, looking actually if we can also estimate lineage-specific diversification rates. And there the idea is that we have the same sort of the process here for the complete phylogeny, and we have speciation events here, but we can have also rate shifts events here. And we can have rate shift events at different parts in our tree. And one of the problems that we have under this process is that actually this rate shift event we didn't really observe, or we don't have in our reconstructed process. But if we specified this as our forward in time process, we always specify that there's an exponential distributed waiting time until there's a speciation event, until there's an extinction event, but also until there's a rate shift event. So it could just happen that there's a speciation event, then there's a speciation event, then there's actually the rate shift event. And this is just how the forward in time process is. And this is when we reconstruct it. There could always be the situation that there are rate shifts at our extinct lineages. So we really need to take that one into account into our computations, that extinct lineages, could have rate shifts. There are some examples where this has been applied, but using slightly different process. So as implemented in BAM, you get especially really colorful pictures there, where diversification rates change a lot through time. I was just using that figure as an example to show you that there's a lot of expectation that diversification rates change through time quite a lot, although I think that is slightly too much estimated variation than we're actually getting. But there's also other ones where we see that diversification rates really change more drastically, and we can also estimate at which points in time or at which clades those diversification rates, those shifts have occurred. In RevBayes, you won't really be able to directly say where these diversification rate shifts have occurred, because I think the most tricky part is to say, were there like a few very small rate shifts, or was there one large rate shift? And we can't really distinguish that well between these different types of rate shifts. That's why it's much more important to just look at what the diversification rates through time are, and then you can say, well, in this clade they are twice as large as in this clade, so they are different, or like you can really just compare directly the rates, but we can't really say how many events have led to that difference. So what is that was, again, what were the modeling issues that we had in BAM when we tried to look into what the actual process is. Then this is what the described process there was, because there it was not assuming that there's rate shifts at extinct lineages, which because we simulate under these type of, we assume these type of processes, that is what you actually need to take into account as well. But then also a problem is that it's always sort of then assuming sometimes that rate shifts at extinct lineages actually happen at exactly the same time and with the same magnitude as at the observed lineage. And then if you sort of flip this lineage, that means that is the neighboring lineage. So if you just flipped your tree a little bit, so it's exactly the same topology, and then under this scenario, you wouldn't expect anymore that there was a rate shift. So it's a little bit tricky if you do apply these kind of assumptions. That is why we are really trying to work more on the actual process, saying that there are rate shifts at the extinct lineages that can happen that are completely independent of other parts. The problem with that is if we have rate shifts that are happening and are drawn from a continuous distribution, we would need to integrate for these extinct lineages over all the possible number of rate shift events, which are already infinitely many, but also we would need to integrate over the infinitely many possible new rates that were drawn from that prior distribution once a rate shift occurred. And this is something we can't really do even numerically. So what we are doing instead, we are assuming that there's a fixed number of rate categories. And in our implementation, that is just you a priori specify how many rate categories do I have. And then you're going to apply that model and estimating that there were rate shifts, and these jumps were just between one of these n rate categories. So in principle, you could test if there were 4 rate categories, or if there were 10 rate categories, or something like that. Just the more rate categories that you're using, the slower the software will run. It's sort of in the idea here also quite similar to what we are doing with the rate variation among sites. So there we always use the gamma model, and we have the gamma distribution, or here log normal distribution, and we discretize it in 4 rate categories. So if we have the log normal distribution with a small variance, then these would be my 4 different rate categories. If I have a larger variance, then those would be my 4 categories. If I want to have a more fine-tuned rate categories, then I specify 10 rate categories here. I have a larger variance, then those would be my 10 quantiles of that log normal distribution. And this is sort of just our way of discretizing and therefore approximating what the actual continuous distribution is, but that actually helps us to do the numerical computation. So it's just an approximation of the real process. The way that we're doing that is we're using exactly the same approach as in the BISI type, so the binary state dependent speciation and extinction rate model, that we're computing the probability that we observed a lineage here using numerical integration. So in this example here, we compute the probability that there was no speciation event, or that there was one speciation event and the left lineage went extinct, or that there was a speciation event and the right lineage went extinct. Then to compute these probabilities that a lineage went extinct, so really computing that extinction probability, it could be that there was an extinction event in that time interval. We also compute that there was a probability that there was no event, and then the time, that the extinction event happened more recently, or that there was a speciation event and then both lineages go extinct. But we are also in those examples taking into account that there was a rate shift event actually at one of the extinct lineages, and then with a new rate category, that one goes extinct more recently, so closer to the present. In the examples that we have here on the observed lineages, we are not directly integrating over rate shift events because we're actually mapping, so we use data augmentation to map where those rate shift events occur. So those are like the speciation events, they are observed events because it's data augmentation. And that's why we don't need to integrate in the likelihood over our over the extinction events. We use the MCMC algorithm to add and remove those rate shift events, and we use the MCMC algorithm to estimate when and where they have happened. So the graphical model for this type of analysis looks slightly more complicated, but not much more than the other diversification rate processes, because what you're specifying is specify a prior distribution on the mean of that rate category that we're discretizing. Then you specify how many rate categories you have, and then you use the discretized distribution function, like the discretized gamma function, to just specify how many diversification rates do I have, or what are the actual diversification rates in each of the categories, and you do the same for the turnover rates. Then you just do your standard, exactly the same, the parameter transformation from the diversification rates and turnover rates to get speciation and extinction rates, and then you just throw that in again into your birth-death process. So in that sense, it's really following exactly the same ideas and outline that we had before. So then once we have that, and what Emma is going to talk more about later, just still have that from my previous slides, is the idea that in the end our goal was we're estimating if diversification rates change through time, were correlated with some environmental factors, changed among lineages, and then were dependent on some morphological characters. So we have a character-dependent diversification rate models as well, and here we see that we want to estimate if speciation and extinction rate depend on compatibility or self-incompatibility. Yes, Emma will talk more about that example. There's also other example where you have the topads and see if the topads are related with diversification rates. You see that you get different estimates of the speciation rate depending if you're padless or if you're pad bearing. You get different extinction rate estimates. And so it's really sort of the same kind of idea that I was just introducing before for the lineage-specific diversification rates. Just now that you're saying, okay, the diversification rates actually don't necessarily change just at a lineage independently, but they change at a lineage depending on how that character changes. There's another example for the squamates where you can really see the difference in estimated speciation and extinction rate. So sometimes we get a lot of signal, sometimes you get a little bit less signal. The example that I have been working on with Will and two other collaborators is the hypothesis that the invasiveness of the placenta is correlated with the speciation rate. So there the idea really is that the more invasive the placenta is, that this is driving reproductive isolation, because if there was a little bit of population differentiation, and that is leading to some mutation and changes, and then you have hybridization happening, that this won't generate any valid offspring because there's too much blood exchange between the mother and the offspring, and therefore you have reproductive isolation. So that's why if we have the epitheliochorial placenta that has the most cell layers, so the least invasive one, the hypothesis would be that this has the lowest diversification rate. The endotheliochorial one has just a few cell layers, and the hemichorial one has the strongest, the most invasive exchange. And we tried to apply that to placental mammals, setting up then the model that we have. If you're in state 1, you have one set of speciation and extinction rates. If you're in the endotheliochorial state, you have the speciation rate 2 and the extinction rate 2. And then if you're in the third state, so that you have a third state of speciation and extinction rates. So you can just go between all the different states, and we try to estimate how speciation and extinction rates are there. I also tried to estimate first, just a little bit to get an overview, is there actually any variation in the diversification rates over the tree? And if you look at that mammalian phylogeny, probably with the colors here you can't see it that well, but there's some rate variation. So if there wouldn't be even any rate variation among lineages, independently of the characters, then I don't even need to test if the character is dependent with those rate variations. That's why we try to work now harder to get actually good estimates on lineage-specific diversification rates estimates first, and then trying to incorporate that much more in these models. But you will also get examples for this one. Yeah.
So it seemed like there were 3 categories here in the tree on the right. So if you
Yeah.
tell the analysis there's going to be 3 categories, won't it always assign some lineages to each of those categories?
Not necessary, no. So if I would, I don't remember how many categories I used for this, but quite often it is the case that, for example, if I say there's 10 rate categories, but I only infer that there's one rate shift. So then I will color all the background branches in one rate category, so in one color, and then there was one rate shift, so that will be the second color. So I'm inferring that there's like 2 different rates that I see, because there was just one rate shift that I mapped on the tree.
So what happens with the other categories? You just get assigned no rates?
Well, Yeah, they're getting assigned no branches. So you really have to assume that on this tree, what I'm doing, I'm trying to estimate was there a rate shift or not. And in my MCMC, I'm dropping always rate shifts, a lot of rate shifts on there, and then I'm removing rate shift. And if there's just no rate shift into that category, then that rate category wasn't occupied. Like there's no lineage that belongs to that rate category. That's why I could infer, or usually infer less rate categories than there are or I'm using in my model. Yeah. The pardon? Oh, okay. So the output for this one, what I did was I looked at this in Fig tree. So the output from RevBayes you can load into Fig tree and then specify to color code the branches according to the average speciation rate that I estimated in RevBayes. So that's one way. I don't know if there's some ways in R that we have set up to do that too right now.
To visualize the shifts?
Yeah, or just generally speciation and extinction rates over among lineages.
The stochastic
Okay.
That's what the purpose of that. It would show
Yeah.
where they shift.
Okay, which I think means that there are other ways that we have, that we are working on, but we don't have examples, for, especially not directly for this. So Will has some examples where you do character mapping. So on, for example, where transitions between in exactly this type of model actually are happening, and then you color that or use our R package to just visualize that kind of nicely. But since there I didn't use, I just tried to estimate lineage-specific diversification rates first without looking at the character. I think we just need to add that to the output. Okay, so the first type of analysis that we did was actually also looking at the ancestral state estimation. And one of the interesting things there is the question, what was the ancestral state for all placental mammals? And what you can see if you use a very simplified model, then you're estimating that the ancestral state was the most invasive, so the hemichorial state, so the blue one over here. And this is just the same tree trimmed to a family level so that you can see it better, but I used the full tree. Or if you actually use a 6-rate model, so you have 1 rate, the 2nd rate, 3rd, 4th rate, 5th, and 6th rate, so all rates can be completely independent, so that would be the full model. Then you estimate that the 2nd state, so the green one here, so the endothelial state was the most probable state to be the ancestor state of all placental mammals. An interesting feature there is that we can also see that it's more supported to be an irreversible model. So you start at the endothelial state, and then you're going to the hemichorial or to the epithelial state, but you're never returning back. So it's really just that directional one, which you can see. So one way to look at it would be with the ancestral state reconstruction, but the other way would be also with Will's method for stochastic character mapping to actually see that those are really just directional changes that we're observing. And it's kind of nice to see that we only get that pattern if we use a full model. And if we could do Bayes factors to actually test between these different models, and we see that the more complex model is in these cases supported. Then the original idea, as I said, was looking at the diversification rates. And here we see that the net diversification rate is much higher for the hemichorial state. So, which means that our hypothesis that the most invasive placenta type seems to be supported in this case, that this is leading to higher net diversification rate. One of the problems was that, well, there might be a lot of background rate variation which could have influenced our diversification rate estimates, and we're just overfitting the models because we said all the rate variation must occur with shifts in our, or changes in our observed characters, so the placenta type. So what we did additionally then, we said there's an unobserved, a hidden character, which represents hidden background rate variation. And we see that there seem to be two classes, two background classes, because we only allowed like a fast and a slow rate as a background. But even if you allow that, you see that still it's always, this is the hemichorial state, and here's the hemichorial state in both cases. Even if you account for background rate variation, it still is much larger than any of the other two states. So what we are seeing is that there's other factors driving diversification rates in placental mammals stronger than the placenta type, but it seems as if the placenta type still has a large effect on diversification rates. So in the summary, what I talked now about was that we have these four different types of processes in RevBayes for the tutorials, and that was the constant diversification rates, so that was the tutorial that you just finished, diversification rates through time, the character-dependent diversification rates, and branch or lineage-specific diversification rates. And for the tutorials that we have, I think you should just try to go through the tutorials as far as you're getting before lunch, before we take the picture. We started with this one, the constant rate birth death process. Then there's the episodic rate birth death process that goes through the autocorrelated model. So what we are setting up here, we're trying to estimate how the diversification rates shift through time. So you're really trying to specify this little model. So let me make that larger. So the main feature here, what you're going to do is you're going to say we have you have a standard deviation, so the change in the speciation rate from one time interval to the next, and for the extinction rate, then you specify a uniform prior distribution on the logarithm of the speciation rates and extinction rates. And here we use the logarithm of these rates because if we then take the exponent of it, that means that the rate must be positive, because speciation and extinction rate must be positive. And the reason also is that we use a Brownian motion, and Brownian motion is generally defined on the full real line, so it can be positive or negative, but we only want to have positive rates, so that's why we use the Brownian motion on the logarithm of speciation and extinction rates. So it's like a geometric Brownian motion or geometric random walk. And then for all the time intervals that we are specifying, so this is the nice thing that you can also just easily say I'm using 5 time intervals or 10 or 20, which is one of the exercises in this tutorial, and specify that my speciation rate in that time interval depends on the log speciation rate at the previous time interval, and the variance of that normal distribution is just the variance or the standard deviation that I specified here, a parameter that I'm estimating as well. And then you're providing the time intervals, so the steps that you had. I'm multiplying this by 0.8, so I'm saying there's no rate shift at the last 20% of the tree, so the earliest 20% of the tree, because that is where you usually don't have much information. But we actually checked, and it works if you just try to estimate rate variation on the entire tree, because it's the autocorrelated process, so the expectation is that always speciation and extinction rates stay the same through time, which helps you instead of saying like, well, speciation and extinction rates are drawn from the same distribution but are independent in every single time interval. And then instead of using the standard birth death prior, use the episodic birth death prior and pass in the speciation rates, the vector when those speciation rates change. The same for the extinction rates, and otherwise it's exactly the same. So you have your sampling probability, sampling strategy, the condition, and pass in the taxa that you have, clamp it, and you run the analysis. If you're going to do that, we have then, there's all the explanation to it, but it's basically exactly the same what you did before. did for that previous tutorial. Then we have a little R script. If you just would run these parts in our R package, well, the RevGadgets packet, where if you go to a
There's a link on the RevBayes workshop website. I think it's below the character dependent diversification rate for how to install the RevGadgets R package.
for
So scroll, I think it's down a little bit.
here.
Yes, there.
So there's the link to it, and it says if you go to the RevGadgets, it tells it's post-processing of the RevBayes output. This is the way how you install it. There's something with GG tree that we're using, so you need to install the tool, but it should be mostly straightforward to just install that R package. And what you can do with that is you can estimate the sort of nice-ish, maybe not so nice-ish yet, outputs and visualization of diversification rates through time. But here you see that I took a very large time interval. The smaller you make the time interval, the nicer and more continuous you get the estimates. And so yeah, if you're interested then about the lineage specific or branch specific diversification rates, that is, that is this tutorial, the next one, but on this tree with 200 taxa and all those, the numerical integration that it does, it runs for an hour until you actually finish it. So if you just wanted to have a look into it, you could start it before lunch and you might get some results once you're coming back from lunch, which then, I think I have output for it in here. Do we? That's the second part. No. Yeah, we are first testing actually how many different rate categories we have. I didn't include any of the visualization. But okay. So I would just suggest if you're just continuing with these tutorials as far as you get, and yeah, if you have any questions, just let me know.